Welcome back to another journey through the cosmos. Tonight, we're travelling to the edge of visibility itself to explore quasars, the brightest beacons in the universe, shining across billions of years of space and time. If you're enjoying these quiet expeditions through science, I'd love it if you take a moment to like this video and subscribe to the channel, and let me know in the comments what topics you'd like me to explore next. Your curiosity helps guide these nocturnal wanderings. Now let's begin. There's something almost incomprehensible about brightness when you really think about it. We understand a candle, we understand the sun, even though it's almost too bright to look at. But quasars are the brightest objects in the entire universe, outshining entire galaxies containing hundreds of billions of stars. Not just brighter than our galaxy, not just twice as bright. A single quasar can be 1,000 times more luminous than the Milky Way. And here's what makes it even stranger. All that light, all that incomprehensible brilliance comes from a region smaller than our solar system. Imagine taking the light output of 1 trillion suns and concentrating it into a space you could, theoretically, cross in a few hours if you were travelling at the speed of light. It's the universe's way of proving that size and power don't always correlate the way we expect them to. Sometimes the smallest regions produce the most dramatic effects. When you look up at the night sky, every star you see is in our own galaxy, relatively close by cosmic standards. But quasars? They're so far away that their light has been travelling for billions of years to reach us, and yet they're still bright enough to be spotted by our telescopes. It's a bit like seeing a candle flame from across an entire continent. The sheer energy required to remain visible across such distances is difficult for our everyday minds to grasp, and maybe that's okay. Maybe some things are meant to inspire awe rather than complete understanding. The name quasar is short for quasi-stellar radio source, and there's a story hidden in that name. When astronomers first spotted these objects in the 1960s, they looked like stars through their telescopes, single points of light, nothing unusual about their appearance. But when they pointed radio telescopes at the sky, something strange emerged. These stars were screaming in radio waves, far more powerfully than any star should. It was a mystery wrapped in confusion. Stars don't behave this way. Stars emit some radio waves, sure, but not like this. Not with this intensity, this fury. So astronomers were left with objects that looked like stars but acted like something else entirely. Something they'd never encountered before. Quasi-stellar. Star-like. But not quite. The name stuck even after we figured out what they really were. A linguistic fossil from an era of profound cosmic confusion. There's something humbling about realizing that some of the brightest objects in the universe were once misidentified as ordinary stars. It reminds us how much our understanding depends on our instruments, on the wavelengths of light we choose to observe. In visible light, quasars were just dots, but in radio waves, they reveal themselves as something far stranger, far more powerful. Perhaps there are still objects in the sky we're looking at right now, thinking we know what they are, waiting for the right telescope or the right idea to reveal their true nature. So what are they really? These quasi-stars that aren't stars at all? Quasars are powered by supermassive black holes feeding on matter at the centres of distant galaxies. And when I say feeding, I mean a cosmic feast of unimaginable proportions. Gas, dust, entire stars sometimes, all spiralling inward toward the black hole, doomed to fall past the point of no return. But here's the beautiful irony. Black holes themselves don't produce light. They're the darkest objects imaginable, regions where gravity is so intense that not even light can escape. So how does a black hole power the brightest objects in the universe? The answer lies not in the black hole itself, but in the material falling toward it. As gas spirals inward, it doesn't fall straight in. It forms a swirling disk, an accretion disk, and the particles in this disk rub against each other, friction heating them to millions of degrees. At those temperatures, matter glows. It shines across the electromagnetic spectrum from radio waves to X-rays, pouring energy into space. It's one of the universe's most elegant transformations, gravitational potential energy converted into light and heat. The process is so efficient, so powerful, that a region smaller than our solar system can outshine 100 billion stars. The black hole itself remains dark, hidden at the centre, but the maelstrom of matter around it blazes like a cosmic beacon, visible across half the observable universe. In a sense, Quasars are the shadows casting light, darkness made luminous by the very act of consumption. The first quasar was discovered in 1963 by an astronomer named Martin Schmidt. He was studying what appeared to be a strange radio source, trying to make sense of its spectrum, the rainbow of light it emitted, broken down into individual wavelengths. At first, the spectrum made no sense. The patterns were all wrong, shifted in ways that didn't match any known elements or any known astronomical object. Then Schmidt had a realization. What if the spectrum wasn't wrong? What if it was just shifted, red-shifted, by an enormous amount? The light from this object had been stretched by the expansion of the universe itself, which meant it was moving away from us at tremendous speed. And the only way it could be moving that fast was if it were incredibly, almost unbelievably, distant. When he calculated the distance, Schmidt realized this star was billions of light years away. And if it was that far away and still visible, it had to be producing an almost incomprehensible amount of light. His discovery didn't just reveal a new type of object, it revealed that the universe contained phenomena far stranger and more energetic than anyone had imagined. Before quasars, the cosmos seemed more orderly, more predictable. After quasars, astronomers had to accept that there were processes out there, violent, brilliant, extreme, that pushed physics to its limits. Schmidt's insight opened a door, and behind it was a universe wilder and more magnificent than we dared to dream. Most quasars we observe existed billions of years ago, when the universe was young and wild. This is one of those facts that sounds simple, but unfolds into something profound the longer you sit with it. When we look at a quasar through a telescope, we're not seeing it as it is now. We're seeing it as it was when the light left it, sometimes 10 billion years ago, sometimes more. The quasar itself might have faded by now, gone quiet, its black hole having consumed all the nearby matter and settled into a calm old age. But we don't see that. We see its youth, its violent prime, preserved in light that has been travelling through space for most of cosmic history to reach our telescopes tonight. In a very real sense, quasars are time capsules. They show us what the universe looked like when it was a fraction of its current age, when galaxies were still colliding frequently, when supermassive black holes were gorging themselves on abundant fuel. There's something almost poetic about it, don't you think? The light falling gently on a telescope mirror today left its source when the universe was a different place entirely. It travelled through expanding space, through clouds of gas and dust, perhaps passing near other galaxies, other stars, witnessing cosmic events we'll never know about, and then, billions of years later, it arrives here, carrying information about an epoch we could never visit any other way. We can't travel backward in time, but light does it for us, bringing news from the ancient universe, one photon at a time. Quasars can consume the mass of several Earths every minute, feeding their supermassive black holes in an unending banquet of matter and energy. Try to picture that for a moment. Every 60 seconds, multiple planets' worth of material spirals past the event horizon, lost forever to the black hole's gravity. It's not a gentle process. It's violent, chaotic, turbulent, matter, colliding and heating and radiating as it makes its final descent. And this cosmic feast releases more energy in seconds than our sun will produce in its entire 10 billion year lifetime. Think about that. Our sun has been burning steadily for about 4.6 billion years, and it has roughly another 5 billion years to go. Over that entire span, it will produce a certain amount of energy, warming planets, driving weather, enabling life on at least one world we know of. A quasar releases that much energy in seconds. Not years, not days, seconds. It's the kind of number that breaks our intuition. We're used to thinking of the sun as powerful, and it is, by our standards. But quasars operate on a completely different scale, in a completely different category of cosmic violence. They're not just bright. They're apocalyptically bright, powered by gravitational forces so intense they tear matter apart at the atomic level, heating it until it screams in X-rays and gamma rays. And yet, for all that violence, there's a strange beauty to it. The universe at its most extreme, converting mass into light with ruthless efficiency, following equations that Einstein wrote down more than a century ago. Perhaps that's what makes it bearable to contemplate. Even at these extraordinary scales, physics still holds, the rules still apply. the disk of matter swirling into a quasar's black hole is called an accretion disk, and it glows hotter than the surface of any star. This isn't just hot by Earth standards, where we consider a few thousand degrees remarkable. The inner regions of an accretion disk can reach tens of millions of degrees, temperatures where atoms are stripped of their electrons, where matter exists in a state called plasma, a kind of fourth state of matter beyond solid, liquid, and gas. Different parts of the disk emit different colours, creating a rainbow of radiation from radio waves to X-rays. The outer edges, farther from the black hole, are cooler and emit in the infrared and radio portions of the spectrum. As you move inward, the temperature rises and the disk begins to glow in visible light, red, then yellow, then white hot. Closer still, and it's emitting ultraviolet radiation, then X-rays, the light of matter in its death throes. What's remarkable is that we can study these disks in such detail despite their enormous distances. By analysing the spectrum of light from a quasar, astronomers can map out the temperature and composition of the accretion disk, understanding which elements are present, how fast the material is moving, even the geometry of the disk itself. It's like being able to read the biography of a maelstrom, understanding its structure and behaviour from billions of light years away. And perhaps what makes accretion disks most fascinating is that they're the visible part of an otherwise invisible process. The black hole itself produces no light, reveals itself only through its gravitational effects, but the accretion disk is the evidence, the proof of the black hole's existence, a glowing signpost pointing to the darkness at the centre. In that sense, accretion disks are how black holes announce themselves to the universe, saying, "I am here, I am feeding, and this is what it looks like when gravity wins." Quasars were much more common in the early universe than they are today. When we survey the sky and count quasars at different distances, which is the same as looking at different epochs in cosmic history, a pattern emerges. The universe's quasar era peaked about 10 billion years ago, a time when galaxies were colliding more frequently, and supermassive black holes had more to eat. Back then, the universe was a more crowded place. Galaxies hadn't spread out as much as they have now. Dark energy hadn't yet begun to dominate cosmic expansion. Gas and dust were more abundant, more available to feed the hungry black holes at galactic centres. And so quasars blazed by the hundreds of thousands, perhaps millions, lighting up the cosmos with their ferocious brilliance. But as the universe aged, things changed. Galaxies consumed or expelled much of their gas. Collisions became less frequent as space expanded and structures spread apart. The black holes at galactic centres, having gorged themselves during the quasar era, ran out of readily available fuel. One by one, quasars began to fade, their accretion disks thinning, their light dimming until what remained were quiet, supermassive black holes, sitting dormant at the hearts of galaxies, waiting for some new influx of matter to awaken them. Today quasars are rare. Oh, we still find them, hundreds of thousands have been catalogued. But compared to the peak era, they're uncommon. We live in a universe past its most violent, most luminous phase, in a calmer epoch where black holes mostly sleep. And there's something almost melancholic about that, isn't there? The universe's wild youth is behind it, preserved only in the light from distant quasars, echoes of a time when the cosmos was louder, brighter, more chaotic. Perhaps that's the fate of all things, to burn brightly for a while, then settle into a quieter existence, remembered only by the light they sent out during their prime. Some quasars shoot out jets of particles travelling at 99.9% the speed of light, extending for millions of light years into space. These jets are among the most impressive structures in the entire universe, narrow beams of matter and energy, launched from the vicinity of the black hole and maintaining their coherence across distances that dwarf entire galaxies. How do they form? The process involves magnetic fields twisted by the spinning black hole, creating cosmic particle accelerators more powerful than anything humans could ever build. As the accretion disk rotates, it drags magnetic field lines along with it, winding them up like a spring. Eventually, these twisted fields snap, releasing enormous amounts of energy and channeling particles outward along the black hole's rotational axis. The particles are accelerated to nearly the speed of light, forming two oppositely directed jets that pierce through the surrounding galaxy and out into intergalactic space. What's extraordinary is that these jets remain focused. They don't spread out or dissipate quickly. They maintain their narrow beam-like structure across millions of light years, creating glowing lobes where they eventually collide with intergalactic gas. We can see these lobes in radio observations, vast bubbles of energized particles marking the endpoints of the jets, sometimes larger than the galaxy that produced them, and the speed, 99.9% the speed of light. At those velocities, relativity becomes important. Time dilates, lengths contract. From the perspective of a particle in the jet, the journey across millions of light years might seem much shorter, time passing differently than it does for stationary observers. It's physics at its most extreme, nature pushing matter to the very edge of what's possible under the laws that govern our universe. Perhaps these jets are a reminder that the universe doesn't share our sense of moderation, our preference for the middle ground. When nature decides to accelerate particles, it doesn't settle for half measures. It goes nearly all the way to the ultimate speed limit. The most distant quasars visible to us are over 13 billion light-years away, existing when the universe was less than 1 billion years old. Let that sink in for a moment. The universe is about 13.8 billion years old now. These quasars were shining when it was less than 1 billion years old, when it was just a child, cosmically speaking, still in the earliest phases of structure formation. Their light has been travelling toward us for most of the universe's existence, carrying messages from the cosmic dawn. When that light began its journey, there were no planets around those distant quasars. There was no Earth, no Sun, no Milky Way as we know it today. The light travelled through expanding space, its wavelength stretching as the universe grew, passing through clouds of primordial gas, witnessing the formation of the first large-scale structures. And then, billions of years later, after crossing an expanse of space so vast it challenges comprehension, those photons arrive at Earth, falling onto the mirrors of our telescopes, carrying information about what the universe was like in its infancy. It's one of the most profound gifts the cosmos offers us, the ability to look backward in time simply by looking far away. Distance equals history in astronomy. The farther we look, the further back we see. These ancient quasars tell us something puzzling though. Their supermassive black holes were already billions of times the mass of the Sun when the universe was very young. How did they grow so large so quickly? It's one of the mysteries we'll explore more deeply as we continue. But for now, just consider the wonder of it. We can see objects that existed before our planet formed, before our star ignited, preserved in light that has travelled across most of cosmic history to reach our eyes. Perhaps that's what makes astronomy so captivating. It's not just about understanding space, but about understanding time, about finding ways to witness epochs we could never visit any other way. Quasars help to prove that the universe is expanding, because their light is shifted toward the red end of the spectrum. This red shift, as it's called, is one of the most important discoveries in all of cosmology, and quasars played a crucial role in confirming it at the largest scales. Here's how it works. When a light source moves away from you, its wavelengths get stretched out, shifted toward the red end of the spectrum. You've probably experienced something similar with sound. An ambulance siren sounds higher pitched as it approaches and lower pitched as it moves away. That's the Doppler effect. Light does the same thing, but instead of changing pitch, it changes colour. Light from objects moving away from us gets redder. Light from objects approaching gets bluer. When Martin Schmidt first decoded the spectrum of that first quasar in 1963, the redshift was enormous. The light had been stretched so much that familiar spectral lines appeared in completely unexpected places. And this redshift told astronomers something profound. The quasar wasn't just moving through space away from us. Space itself was expanding, carrying the quasar along with it. The expansion of the universe, predicted by Einstein's equations and first observed by Edwin Hubble, was real and operating on truly cosmic scales. Quasars became distance markers, cosmic signposts scattered throughout the universe at various epochs. By measuring their redshift, astronomers could determine how far space itself is stretching, how the expansion rate has changed over time. Some quasars showed moderate redshift, indicating they were relatively nearby, though still billions of light years away. Others showed extreme redshift, indicating they existed when the universe was a fraction of its current size. Each quasar became a data point in the story of cosmic expansion, helping us understand not just that the universe is growing, but how it has grown over billions of years. And all of this information encoded in something as simple as the colour of light, in the stretching of wavelengths across the expanding fabric of space. A typical quasar's central black hole weighs as much as millions or billions of suns compressed into a space smaller than our solar system. The numbers are almost absurd when you first encounter them. Take 1 billion stars like our Sun. Now compress them, all their mass, all their matter, into a region you could cross in a few hours travelling at the speed of light. The density becomes incomprehensible, a concentration of mass so extreme that it warps space-time into shapes we can barely visualise. This is what creates the black hole's defining characteristic, an event horizon, a boundary beyond which gravity is so strong that nothing, not even light, can escape. For a black hole with 1 billion solar masses, the event horizon might have a radius of a few billion kilometres, large by human standards, but tiny compared to the size of a galaxy, or even compared to the distances between stars. What happens to space near such an object? It curves, dramatically. Einstein's general relativity tells us that mass warps the fabric of space-time, creating what we perceive as gravity. Near a black hole of this magnitude, space-time is bent so severely that it essentially forms a pit, a gravitational well so deep that falling in means never coming back. Light itself follows the curves of space-time, and near the event horizon, those curves become so steep that all possible paths lead inward. And yet, despite this extreme density, despite this incomprehensible concentration of mass, the black hole itself is remarkably simple. It has mass, it has spin, and if it's electrically charged, which most probably aren't, it has charge. That's it. All the information about what fell in, whether it was hydrogen gas or iron or entire stars, is erased. The black hole remembers only the total mass, the total angular momentum, the total charge. Everything else is lost, hidden behind the event horizon. Perhaps there's something almost zen about that simplicity, the way the universe's most extreme objects are also its most minimalist, defined by just a few numbers despite containing the mass of billions of suns. Quasars flicker and vary in brightness over timescales from hours to years, like distant cosmic lighthouses. This variability is one of the ways astronomers first realized these objects were relatively small despite their enormous power. Let me explain why flickering tells us about size. Imagine an object that's a light year across, roughly the distance from the Sun to its nearest stellar neighbour. If something happens on one side of this object, it takes a year for light from that event to reach the other side. This means the object can't change its overall brightness faster than about a year, because different parts of it can't coordinate their behaviour faster than light-speed communication allows. It's a fundamental limit. An object can't flicker faster than the time it takes light to cross it. When astronomers observed quasars varying in brightness over days, weeks, or even hours, they realised something profound. These objects, despite outshining entire galaxies, had to be relatively compact, perhaps only light hours or light days across. The rapid flickering was telling us about size, constraining it through the speed of light itself. It was a beautiful piece of detective work using the tempo of brightness changes to deduce the scale of something billions of light years away. But what causes the flickering? These changes tell astronomers about the turbulent dance of matter spiralling toward oblivion. The accretion disk isn't smooth or uniform, it's chaotic, with clumps of matter, instabilities, magnetic turbulence. Sometimes a particularly dense blob of gas falls in, temporarily brightening the quasar. Sometimes the structure of the disk shifts, changing how efficiently it radiates. Sometimes there are flares, sudden releases of energy from magnetic reconnection events. Each flicker, each variation, is a window into the physics of extreme environments. By monitoring how a quasar's brightness changes over time, astronomers can study the behaviour of matter in gravitational fields 1 billion times stronger than what we experience on Earth. They can probe the structure of the accretion disk, estimate the mass of the central black hole, even detect the effects of relativity as light from different parts of the disk reaches us at different times. The lighthouse doesn't just guide us, it tells us its own story, encoded in the rhythm of its light. The radiation from a quasar can push on gas and dust, creating winds that blow outward at thousands of kilometers per second. This might seem counterintuitive at first. How can light push on matter? But photons, despite having no mass, carry momentum. When they're absorbed by atoms or scattered off particles, they transfer that momentum, creating a pressure. Near a quasar, where radiation is extraordinarily intense, this radiation pressure becomes a powerful force. These quasar winds can halt star formation in entire galaxies, shaping the evolution of cosmic structures in profound ways. Here's how it works. To form stars, you need cold, dense gas that can collapse under its own gravity. But quasar winds heat the gas and drive it outward, away from the galaxy. The gas becomes too hot and too dispersed to collapse into stars. Star formation shuts down, sometimes across the entire galaxy, leaving behind aging stellar populations with no young stars being born to replace them. This process, called feedback, is one of the most important ways that supermassive black holes influence their host galaxies. For a long time, astronomers were puzzled about why the most massive galaxies seemed to stop forming stars billions of years ago, even though they still contained gas. The answer, it turns out, involves the black holes at their centres. When these black holes were active as quasars, their radiation and winds ejected or heated so much gas that star formation ceased. The galaxy and its central black hole reached a kind of equilibrium, with the black hole regulating its own food supply by preventing new stars and new gas from forming. It's a feedback loop on a cosmic scale, and it helps explain one of the great patterns in the universe, the relationship between galaxy mass and black hole mass. Somehow, galaxies and their central black holes know about each other. They grow together, influence each other's evolution, maintain a balance. And quasar winds are part of that conversation, a way for the black hole to speak to its galaxy to say, "Slow down, you're feeding me too much, we need to reach an equilibrium." Perhaps what's most remarkable is that this happens at all, that violent processes at the centre of a galaxy can shape star formation out in the spiral arms, millions of light years away. Gravitational lensing can create multiple images of the same quasar when a galaxy sits between us and the distant light source. This is one of the most visually striking confirmations of Einstein's general relativity, and it turns the universe into a kind of cosmic laboratory where we can test our theories of gravity. Here's what happens. Light from a distant quasar travels toward us across billions of light years. If a massive galaxy happens to lie along the line of sight, its gravity bends the light rays, acting like a lens. But unlike a glass lens, which produces a single image, perhaps magnified or distorted, a gravitational lens can produce multiple images. The quasar's light takes several different paths around the intervening galaxy, each path bent by gravity, and we see the same quasar in several places at once. Even more fascinating, each image shows a slightly different moment in the quasar's history. This happens because the different light paths have different lengths. One path might be, say, a few hundred light years longer than another. That means the light taking the longer path left the quasar a few hundred years earlier. If the quasar's brightness varies, we might see it bright in one image and dim in another, or vice versa, watching the same event happen at different times in different images. Astronomers use this to measure cosmic distances with remarkable precision. By monitoring how long it takes for a brightness change to appear in each image, the time delay between images, they can calculate the exact difference in path length. Combined with models of the lensing galaxy's mass, this gives an independent measure of the expansion rate of the universe. It's called time delay cosmology, and it's one of several methods astronomers use to pin down how fast the universe is expanding, a number that's crucial for understanding cosmic history and fate. But perhaps the most wonderful thing about gravitational lensing is what it represents philosophically. We're seeing the same object multiple times, light from the same source reaching us via different routes through curved space-time. It's a reminder that space isn't a fixed stage where events play out. It's a dynamic entity, warped by mass, influencing how light travels. Einstein predicted this bending in 1915, but he thought it would never be observed, that the effects would be too subtle. He was wrong. The universe provided quasars, bright enough to be seen across cosmic distances, and massive galaxies positioned just right to bend their light, giving us multiple images of the same object, a cosmic gift for testing the limits of physics. Quasars produce more ultraviolet light than any other type of cosmic object, bathing their surroundings in high-energy radiation. Ultraviolet light sits just beyond the violet end of the visible spectrum, with wavelengths shorter than what our eyes can detect but longer than X-rays. It's energetic enough to ionize atoms, to strip electrons away from their nuclei. And this is exactly what quasars do to the space around them. This intense UV light can ionize hydrogen across millions of light years, creating vast glowing bubbles in space. Imagine the universe as a sea of neutral hydrogen gas, atoms with their electrons still attached, invisible and dark. Then a quasar turns on, and its ultraviolet radiation spreads outward like a spherical wave, encountering hydrogen atoms and knocking their electrons free. The ionized region grows, a bubble of glowing gas expanding around the quasar, sometimes reaching sizes larger than entire galaxy clusters. We can detect these bubbles even when we can't see the quasar itself directly. The ionized hydrogen emits light at specific wavelengths, creating a signature that tells us a powerful radiation source must be nearby. It's like seeing the glow of a lighthouse reflected off fog, even when the lighthouse itself is hidden. These ionization bubbles reveal the quasar's influence, showing us how far its radiation reaches, how powerfully it affects its cosmic neighborhood. And there's a historical dimension to this too. In the early universe, after the Big Bang, there was a period called the Cosmic Dark Ages when the universe was filled with neutral hydrogen that absorbed most light. The universe was opaque, foggy, difficult to see through. Then the first stars and quasars formed, and their ultraviolet radiation began ionizing the hydrogen, clearing the fog. This epoch, called reionization, transformed the universe from opaque to transparent, allowing light to travel freely across cosmic distances. Quasars were key players in this transformation, their UV radiation helping to make the universe the clear, visible place it is today. Perhaps that's one of their most important legacies, not just being bright, but being so bright that they changed the very nature of space itself, clearing the fog so that light could travel, and we could eventually look back and see them. The supermassive black holes powering today's dead quasars likely still exist at the centers of most large galaxies, including our own. This is one of those realizations that changes how you think about the night sky. When you look at a galaxy through a telescope, say the Andromeda Galaxy, that beautiful spiral visible from Earth, there's probably a supermassive black hole at its center, a remnant of a time when that galaxy hosted an active quasar. The Milky Way's central black hole is quiet now, a sleeping giant that once might have blazed as a quasar. We call it Sagittarius a star, and it weighs about 4 million times the mass of the Sun. That's substantial, but it's not feeding actively. There's some gas and the occasional star wandering too close, but nothing like the torrents of matter that fell in billions of years ago. Sagittarius. A star is dormant, producing only faint emissions, nothing like the blinding light of a quasar. But the potential is still there. If something disrupted the galaxy, a collision with another galaxy perhaps, or a sudden influx of gas from some other event, Sagittarius A star could awaken. It could begin feeding again, becoming an active galactic nucleus, maybe even a quasar if the fuel supply were sufficient. The black hole itself hasn't gone anywhere. It's just waiting, patient, eternal, ready to consume whatever comes within reach. This means that when we look at distant quasars, we're not seeing exotic objects fundamentally different from what's nearby. We're seeing what many galaxies, including our own, probably looked like billions of years ago. The quasar era wasn't happening somewhere else in a different kind of universe. It was happening here, in the same space where we now live, just at a different time. Our galaxy's central black hole was probably once as luminous as the quasars we observe now. It's quieted with age, but the machinery is still there, the capacity for violence still present, just dormant. Perhaps there's something comforting about that, about knowing that even the most extreme phenomena have life cycles, that they don't rage forever. Quasars burn bright and then fade. Black holes feed and then sleep. The universe's wild youth gives way to a calmer middle age, and maybe that's okay. Maybe even black holes deserve a rest after billions of years of cosmic fireworks. Quasars were crucial in helping astronomers map the structure of the early universe and understand how galaxies formed. They act as beacons shining through cosmic time, illuminating the gas and matter between us and them. And it's this illumination of the intervening material that makes quasars so valuable as cosmic probes. When light from a quasar travels toward Earth, it passes through clouds of gas in intergalactic space. Each cloud absorbs light at specific wavelengths corresponding to the elements it contains: hydrogen, helium, carbon, whatever is present. This creates absorption lines in the quasar's spectrum, dark gaps where light has been absorbed. By studying these absorption lines, astronomers can map out the distribution of gas between us and the quasar, understanding how matter was distributed in the early universe. There's a particular feature called the Lyman alpha forest, a series of many absorption lines caused by neutral hydrogen at different distances. It looks like a forest of lines in the spectrum, each one representing a cloud of hydrogen somewhere along the line of sight. By analysing this forest, astronomers can reconstruct the web-like structure of matter in the early universe, seeing how gas was distributed in sheets and filaments rather than uniformly spread out. This was revelatory because it showed that structure formation began early. Even billions of years ago, matter wasn't distributed smoothly. It was already clumping, already forming the cosmic web that would eventually give rise to galaxies and galaxy clusters. Quasars provided the backlight that made this structure visible, like shining a flashlight through a dusty room and seeing all the particles floating in the air. And the farther away the quasar, the earlier the epoch we can study. The most distant quasars show us what the universe was like less than 1 billion years after the Big Bang, during the era of reionization, when the first large structures were forming. Without quasars, we'd have far less insight into this crucial period of cosmic history. They're not just interesting objects in their own right, they're tools, cosmic lighthouses that allow us to study everything between them and us. Perhaps that's the best gift a bright object can give, not just to shine, but to illuminate everything around it, making the invisible visible, turning darkness into data. Some quasars change their classification over time, fading into less active galactic nuclei as their food supply diminishes. They're not eternal. Like stars, they have life cycles that span millions to billions of years. This gradual fading happens as the black hole consumes or expels the gas in its vicinity, leaving less material available to fall inward and power the brilliant accretion disk. The transition isn't always smooth. A quasar might flicker through different states, bright one epoch, dim the next, sometimes brightening again if new material becomes available. Astronomers have observed what they call changing look quasars that shift from one type to another over timescales of years or decades, much faster than we once thought possible. These rapid changes suggest that the boundary between an active quasar and a quieter state is more fluid than previously believed, dependent on the vagaries of gas supply and the complex dynamics of the accretion disk. Eventually, though, most quasars settle into retirement. The accretion disk thins and cools. The brilliant jets fade or shut off entirely. What remains is a supermassive black hole in a relatively quiet state, perhaps still accreting a trickle of matter, but nothing like the torrents of its youth. The galaxy around it continues evolving, stars living out their lives, new stars forming if gas remains, but the central engine that once outshone everything else grows quiet. This life cycle matters because it connects the past to the present. The dead quasars of today were the blazing beacons of yesterday. The quiet black holes we find in nearby galaxies were probably active billions of years ago, during the peak of the quasar era. Nothing lasts forever, not even the brightest objects in the universe. They burn through their fuel, exhaust their food supply and settle into dormancy. It's a reminder that even cosmic phenomena are temporary, that the universe changes not just through expansion, but through the evolution of individual objects, each following its own arc from birth through activity into quiet old age. The radio jets from quasars can influence star formation in galaxies millions of light-years away. This is one of those facts that illustrates just how far-reaching a quasar's influence can be. We've already talked about how quasar winds can affect the host galaxy, but the jets, those narrow beams of particles travelling at near light speed, can reach far beyond, punching through intergalactic space and affecting entirely different galaxies. When a jet slams into a distant galaxy, it compresses the gas there, and compressed gas can trigger star formation. It's like squeezing a sponge. Concentrate the material enough, and gravity takes over, pulling it together into dense clumps that can collapse into stars. So ironically, even though quasars often shut down star formation in their own galaxies through feedback, they can stimulate it elsewhere, in galaxies that happen to lie in the path of their jets. This makes quasars cosmic sculptors, shaping not just their immediate environment, but the larger cosmic neighbourhood. A single quasar's reach extends far beyond its host galaxy, influencing star formation, heating intergalactic gas, stirring up the medium between galaxies. It's a bit like how a single large tree in a forest, doesn't just affect the ground beneath it, but influences water flow, nutrient distribution, and light availability for other plants nearby. And this influence operates on timescales of millions of years. The jets take time to propagate outward. The effects on star formation unfold slowly, across multiple generations of stars. Long after the quasar itself has faded, its jets might still be compressing gas in a distant galaxy, triggering star formation, creating new stellar nurseries. The quasar's legacy persists, written into the structure and star formation history of nearby galaxies. Perhaps what makes this most fascinating is the interconnectedness it reveals. We often think of galaxies as isolated islands, each evolving independently. But quasars show us that galaxies influence each other across vast distances, that the universe is more connected than it appears, with effects propagating through space in ways both obvious and subtle. A quasar doesn't just affect its own galaxy, it affects the cosmic web around it, shaping structures millions of light years away, leaving fingerprints that persist long after its light has faded. Quasars emit across the entire electromagnetic spectrum simultaneously, from low-energy radio waves to high-energy gamma rays. This is quite remarkable when you think about it. Most objects in the universe have a favourite wavelength, a particular part of the spectrum where they shine brightest. Stars emit mostly visible light and infrared. Cool gas clouds glow in radio waves. But quasars, they do everything at once. To fully understand a single quasar, astronomers must observe it with many different types of telescopes. Radio telescopes detect the synchrotron radiation from the jets and the extended lobes. Infrared telescopes peer through dust to see the warm material near the accretion disk. Visible light telescopes capture the optical glow from the disk itself. Ultraviolet satellites measure the ionizing radiation. X-ray observatories detect the hot inner regions where matter is being torn apart. And gamma-ray telescopes sometimes catch the most energetic emissions from the jets, or the vicinity of the event horizon. Each wavelength tells a different part of the story. The radio waves map the large-scale structure of the jets, showing where they've travelled over millions of years. The infrared reveals heated dust, perhaps in a torus surrounding the accretion disk. The visible and UV light traces the accretion disk itself, showing us the temperature and composition of the infalling matter. The X-rays probe the innermost regions where gravity is strongest and temperatures are highest. And the gamma rays, when present, hint at the most violent acceleration processes, particles boosted to extreme energies by magnetic fields or shock waves. It's like trying to understand a symphony by listening to each instrument separately. The strings tell you one thing, the brass another, the percussion something else entirely. Only by hearing them all together do you grasp the full composition. Quasars are multi-wavelength phenomena, and they demand multi-wavelength observations. They're too complex, too energetic, too varied to be captured in any single band of light. And perhaps that's appropriate for the brightest objects in the universe. They don't whisper in one wavelength. They shout across the entire spectrum, announcing their presence in every possible way, making sure that no matter what kind of telescope you point at them, you'll detect something, you'll learn something new. They're comprehensive in their brightness, thorough in their emission, leaving nothing out, holding nothing back. The matter falling into a quasar's black hole doesn't fall straight in. It spirals inward like water circling a drain. This happens because of angular momentum, a property of rotating systems that's conserved unless something acts to change it. When gas approaches a black hole, it almost always has some sideways motion, some component of velocity that's not purely radial. And because angular momentum is conserved, that sideways motion gets amplified as the material moves inward. Think of an ice skater pulling in their arms to spin faster. The same principle applies here, just on a cosmic scale. As matter falls closer to the black hole, it has to rotate faster to conserve its angular momentum. This prevents it from falling straight in. Instead, it settles into an orbit joining the accretion disk, that vast spiral of doomed material circling the black hole. And this spiral takes time, allowing the matter to heat up and shine brilliantly before its final plunge. The orbital velocity near a black hole can reach significant fractions of the speed of light, sometimes 10%, 30%, even higher in the innermost regions. At those speeds, friction between particles in the disk generates tremendous heat. The material glows, radiating energy across the spectrum, contributing to the quasar's brilliance. The innermost stable orbit varies depending on the black hole's spin. For a non-rotating black hole, matter can orbit as close as about 3 times the event horizon radius. For a maximally spinning black hole, it can get closer, approaching the event horizon more tightly. Inside this innermost stable orbit, there are no stable paths. Matter either falls straight in or is flung outward. So there's a boundary, a last point where matter can circle before it inevitably crosses the event horizon. And in those final moments, in those last orbits before the plunge, the matter is at its hottest, its brightest, radiating furiously as it approaches the point of no return. It's a kind of cosmic swan song, matter announcing itself one final time before disappearing forever beyond the event horizon. The spiral isn't just a geometric curiosity, it's essential to the quasar phenomenon, the reason why black holes, which themselves produce no light, can power the brightest objects in the universe. The delay, the spiral, the friction, these are what make quasars possible. Quasars can outshine their entire host galaxy by 100 to 1, making it nearly impossible to see the galaxy itself. Imagine trying to spot a firefly sitting next to a searchlight. The searchlight's glare drowns out the firefly's faint glow, making it invisible even though it's right there. This is the challenge astronomers faced when trying to study the galaxies hosting quasars. For decades, quasars appeared as point sources of light, just like stars, with no visible surrounding structure. It wasn't clear whether they were inside galaxies at all, or if they were some kind of isolated phenomenon. The glare from the quasar was simply too intense, overwhelming any light from the surrounding stars. It was one of the great frustrations of quasar astronomy, knowing that there must be a galaxy there, but being unable to see it. Only recently have astronomers developed techniques to block the quasar's glare and glimpse the stars around it. One method involves using coronagraphs, special masks that block the bright central light source, similar to how you might shade your eyes from the sun to see the landscape around it. Another technique uses advanced image processing, subtracting out the quasar's light mathematically to reveal the fainter galaxy underneath. And what they found when they could finally see the host galaxies was illuminating. Many quasar hosts showed signs of recent galaxy mergers, distorted shapes, tidal tails of stars pulled out by gravitational interactions, multiple nuclei indicating galaxies in the process of combining. This supported the idea that quasars are often triggered by galaxy collisions, events that funnel gas toward the central black hole, providing the fuel for a period of intense activity. But the difficulty in seeing the host galaxy reminds us how perspective matters in astronomy. From Earth, separated by billions of light years, the quasar and its galaxy are both just a point of light. The quasar's brilliance makes the galaxy invisible, even though the galaxy is vastly larger. It's a reminder that brightness and size don't always correlate, that sometimes the smallest regions produce the most dramatic effects, drowning out everything around them in their intensity. The black holes in quasars grew surprisingly fast in the early universe, reaching billions of solar masses in less than a billion years. This is one of the great puzzles in astrophysics, a timeline that seems almost impossibly compressed. To understand why it's puzzling, we need to think about how black holes grow. A black hole grows by accreting matter, pulling in gas and stars and whatever else comes within reach. But there's a limit to how fast this can happen, called the Eddington limit. When a black hole accretes matter, the infalling material heats up and radiates. This radiation creates outward pressure, pushing against the infalling gas. If the black hole tries to eat too fast, the radiation pressure becomes so strong that it blows away the surrounding material, shutting off the food supply. The Eddington limit is the maximum accretion rate, at which radiation pressure and gravity balance. For a black hole growing at the Eddington limit continuously, there's a characteristic timescale for doubling its mass, roughly 50 million years. So starting from, say, 100 solar masses, perhaps the remnant of a very massive early star, a black hole growing at the Eddington limit could reach 1 billion solar masses in maybe 500 million years or so, through repeated doublings. That's fast, but the most distant quasars existed when the universe was only 600 to 700 million years old. There's barely enough time, and that assumes continuous growth at the maximum rate, which seems unlikely. Scientists are still puzzled about how black holes could grow so massive so quickly after the Big Bang. Perhaps the seed black holes were larger than we think, formed through direct collapse of massive gas clouds rather than from stellar remnants. Perhaps they grew faster than the Eddington limit somehow, during brief periods of super-Eddington accretion. Perhaps our understanding of the early universe is incomplete, and conditions were more favourable for rapid black hole growth than current models suggest. It's an active area of research, with new theories and observations constantly refining our understanding. But for now, the rapid growth of early quasar black holes remains somewhat mysterious, a reminder that the universe's youth was different in ways we're still working to comprehend. Perhaps that's fitting. The brightest objects in the universe, powered by the most extreme phenomena we know of, should keep at least a few secrets. Quasar jets can bend and twist due to the precession of the black hole's spin axis, creating beautiful corkscrew shapes in space. Precession is a phenomenon you might be familiar with from a spinning top. As the top spins, its axis of rotation slowly wobbles in a circle. Black holes can do something similar, especially if they're in binary systems or if the accretion disk is tilted relative to the black hole's spin. When the black hole's spin axis precesses, the jets, which are launched along this axis, follow the wobble. Over thousands or millions of years, this creates twisted helical patterns in the radiolobes. Astronomers observing these jets see beautiful spiral structures, corkscrew shapes traced out by the relativistic particles as the jet's direction slowly changes. These patterns reveal the complex gravitational dance between the black hole and its surroundings. If the quasar is in a binary system with another black hole, the two black holes gravitationally influence each other, causing precession. If the accretion disk is tilted, it exerts a torque on the black hole, slowly changing its spin direction. Either way, the jets record this motion, creating visible structures that astronomers can study to learn about the black hole's environment and history. It's a bit like a cosmic version of a spirograph, those old drawing toys where gears spinning inside each other created intricate patterns. But here the patterns are millions of light years across, traced out by particles moving at nearly the speed of light, recording the slow wobble of a supermassive black hole over timescales that dwarf human history. And there's something aesthetically pleasing about these structures, isn't there? The universe, for all its violence and chaos, still produces patterns, symmetries, shapes that appeal to our sense of beauty. A twisted quasar jet is both a scientific puzzle to decode and a work of natural art, geometry emerging from physics, beauty from mathematics. Perhaps that's one of the quiet joys of astronomy, discovering that even the most extreme phenomena can be elegant, that the universe's violence doesn't preclude its beauty. The closest quasar to Earth is still over 600 million light-years away, which means quasars are exclusively deep space phenomena. There are none in our cosmic neighbourhood, none anywhere nearby on the scale of the universe, and this is frankly quite fortunate for us. We're fortunate they're so distant. A nearby quasar would flood Earth with deadly radiation. Think about what a quasar does to its surroundings. It bathes everything nearby in high-energy ultraviolet light, X-rays, sometimes gamma rays. This radiation is intense enough to ionize atoms across millions of light-years. Now imagine if such an object existed, say, a few thousand light-years away, closer than many of the stars we can see with the naked eye. Earth would be bathed in radiation powerful enough to strip away our atmosphere, sterilize the surface, make the planet utterly inhospitable to life as we know it. The fact that quasars are rare in the modern universe, and that none exist anywhere near the Milky Way, is part of what makes our existence possible. We live in a calm era of cosmic history, in a quiet region of space, far from the violent phenomena that dominated the early universe. Our sun is a stable, middle-aged star. Our galaxy's central black hole is dormant. The neighbourhood is peaceful, allowing planets to form, life to evolve, civilizations to contemplate the distant violence visible only through telescopes. But this distance also means something profound about observation. Every quasar we see is ancient, a relic from billions of years ago. We can't study a nearby quasar up close because there are none. We're limited to distant observations, to light that's travelled across most of cosmic history to reach us. It's like being paleontologists studying dinosaurs. We have fossils, footprints, remnants, but we can't observe the living creatures. We can't see a quasar in real time, only as it was in the distant past. And yet, maybe that's enough. Maybe the universe is giving us exactly what we need: distant examples to study safely, close enough to detect with our telescopes but far enough to pose no threat. We can observe their brilliance without suffering their consequences, learning from their violence without experiencing it firsthand. It's a kind of cosmic courtesy, the universe keeping its most dangerous phenomena at a safe distance, while still letting us glimpse them, still letting us learn. Quasars played a role in reionizing the universe after the cosmic dark ages, when stars first began to shine. This epoch, called reionization, was one of the most important transitions in cosmic history, transforming the universe from opaque to transparent, from dark to visible. Here's what happened. After the Big Bang, the universe was extremely hot and ionized. All the electrons were stripped from atoms, creating a plasma. As the universe expanded and cooled, around 380,000 years after the Big Bang, electrons and protons combined to form neutral hydrogen. The universe became neutral, and this neutral hydrogen absorbed most visible and ultraviolet light, making the universe opaque. This was the beginning of the cosmic dark ages, a period when the universe was dark not because there was no light, but because light couldn't travel freely. Then, several 100 million years later, the first stars and galaxies formed. These first luminous objects began emitting ultraviolet radiation, and this UV light started ionizing the surrounding hydrogen, creating bubbles of ionized gas. Each star, each galaxy, each quasar created its own bubble, and gradually these bubbles grew, overlapped, merged. Over hundreds of millions of years, the entire universe transitioned from mostly neutral to mostly ionized, from opaque to transparent. Quasars were key players in this transformation, their intense radiation helping to clear the fog that filled space in the early universe. A single quasar could ionize a region hundreds of millions of light-years across, contributing significantly to the overall reionization process. And because quasars were brighter than individual stars or even entire galaxies, they were disproportionately important in clearing large volumes of space. This reionization had profound consequences. It allowed light to travel freely, making the universe visible across cosmic distances. It changed the chemistry of intergalactic gas, affecting how future generations of stars and galaxies would form. It essentially created the transparent universe we observe today, where light from distant objects can reach us unimpeded. And quasars were the torches in that darkness, the beacons that helped transform the universe from an opaque fog into the clear, starlit expanse we see tonight. Their legacy isn't just their own brilliance, but the transparency they helped create, the visibility they enabled. Perhaps every time we look through a telescope and see a distant galaxy, we should remember that quasars helped make that observation possible, clearing the fog billions of years ago so that light could travel and we could eventually look back and see them. Some quasars show absorption lines in their spectra, from clouds of gas that happen to be between us and the quasar. These cosmic coincidences allow astronomers to study gas clouds billions of light-years away that we could never see directly. The clouds themselves produce no light, emit no detectable radiation. They're invisible. But when a quasar sits behind them, its light passes through them, and the atoms in the clouds absorb light at specific wavelengths. Each element absorbs light at characteristic wavelengths determined by atomic physics. Hydrogen absorbs in specific patterns, carbon in others, oxygen in yet others. By looking at which wavelengths are missing from the quasar's spectrum, astronomers can determine which elements are present in the intervening clouds, how much of each element there is, how dense the cloud is, even its temperature and motion. And because we can see multiple absorption systems at different redshifts along the same line of sight, we're effectively sampling the intergalactic medium at different epochs in cosmic history. A single quasar spectrum might show absorption from a cloud 8 billion light-years away, another cloud 10 billion light-years away, yet another 11 billion light-years away. Each absorption system is a snapshot of intergalactic gas at a different time, allowing us to trace how the composition and distribution of matter has changed over billions of years. This technique has revealed that the intergalactic medium isn't empty. It's crisscrossed with filaments of gas, enriched with elements forged in stars and expelled by supernovae and quasar winds. These clouds tell us about the history of star formation, about how metals spread through space, about the complex interplay between galaxies and the gas between them. It's accidental astronomy in the best sense. We weren't looking for these gas clouds, but they revealed themselves by getting in the way. And quasars, by being so bright and so distant, provide the perfect backlighting to make the invisible visible. Every quasar spectrum is a treasure trove of information not just about the quasar itself, but about everything its light encountered on its journey to Earth. Perhaps that's one of the most valuable gifts a distant light source can offer, not just showing us itself, but illuminating everything between us and it, turning cosmic coincidences into scientific opportunities. The energy efficiency of a quasar is remarkable. About 10% of falling matter's mass is converted to energy, compared to 0.7% in stars. Let that sink in for a moment. When you burn hydrogen in a star's core, fusing it into helium, you convert about 0.7% of the mass into energy via Einstein's famous equation, E=mc². That's the process that powers the sun, that sustained stars for billions of years across the universe. It's efficient by everyday standards, but it's nowhere near the theoretical maximum. Quasars do much better. When matter falls into a black hole swirling through the accretion disk, something like 10% of its mass energy is converted to radiation before it crosses the event horizon. In some cases, for rapidly spinning black holes, the efficiency can be even higher, approaching 40%. This makes quasars the most efficient engines in the universe, far more efficient than nuclear fusion, more efficient than any energy conversion process we know. How is this possible? It comes down to gravity. Near a black hole, gravitational potential energy is enormous. As matter falls inward, it gains kinetic energy, it speeds up. And when particles moving at significant fractions of the speed of light collide and interact in the accretion disk, they convert that kinetic energy into heat and radiation with remarkable efficiency. The process is powered by Einstein's E=mc², the same equation that governs nuclear reactions, but the efficiency is much higher because the gravitational fields are so much stronger. This efficiency explains how quasars can be so bright. They're not just consuming matter, they're extracting an enormous fraction of that matter's mass energy and radiating it into space. A quasar eating a few solar masses per year can outshine an entire galaxy because it's so efficient at converting mass to light. It's the universe's ultimate demonstration of Einstein's equation, showing just how much energy is locked up in matter, waiting to be released under the right conditions. And perhaps there's something almost elegant about that efficiency. The way nature finds the most effective path from matter to energy near black holes. The universe doesn't waste resources when it makes quasars. It extracts nearly everything available, converting mass to light with ruthless efficiency, following the equations that govern space-time with precision. The result is the brightest objects we know, powered by the most efficient energy conversion process in existence. Quasars were initially thought to be within our own galaxy because no one imagined anything could be that bright from so far away. This misunderstanding, this failure of imagination, is understandable. Before quasars, the most distant objects astronomers studied were other galaxies, each containing billions of stars. To think that a single object appearing as a point of light could outshine an entire galaxy seemed absurd. When the first quasars were discovered in the early 1960s, some astronomers argue they must be nearby, perhaps unusual stars within the Milky Way. Even though their spectra looked strange, even though they emitted powerful radio waves, it seemed more plausible that they were local oddities than objects at cosmological distances. The human mind tends to prefer explanations that fit within existing frameworks, and the framework at the time couldn't accommodate objects billions of light years away that were bright enough to appear stellar. But accepting their true distance required astronomers to fundamentally reconsider what was possible in the universe. When Martin Schmidt decoded that first quasar spectrum and calculated its redshift, the implications were staggering. If the redshift was real, if the quasar was truly that distant, then it had to be producing more energy than anyone thought possible. It meant the universe contained phenomena far more extreme than previously imagined. This acceptance, this expansion of cosmic horizons, changed astronomy. Suddenly the universe was bigger, more energetic, more violent. There were objects out there with luminosities that dwarfed anything in our cosmic neighborhood. The quiet, orderly universe of the mid-20th century gave way to a cosmos filled with supermassive black holes, accretion disks radiating at extraordinary efficiencies, jets traveling at near light speed. And perhaps this is one of the lessons quasars teach us. The universe is under no obligation to match our expectations or our intuitions. It's bigger, stranger, more extreme than we typically imagine. When we encounter something that doesn't fit our frameworks, sometimes the framework needs to expand. Sometimes we need to accept that reality exceeds our imagination, that the cosmos contains wonders we haven't yet dreamed of, that the brightest objects visible across billions of light years are exactly as bright as they appear, regardless of whether that seems possible. The magnetic fields around quasars can be millions of times stronger than Earth's magnetic field. To put this in perspective, Earth's magnetic field is strong enough to deflect the solar wind, protect our atmosphere, and make compass needles point north. It's a gentle field by cosmic standards, measuring about half a Gauss at the surface. But near a quasar's accretion disk, magnetic fields can reach millions of Gauss, sometimes more. These fields channel and accelerate particles into the jets, creating natural particle beams more powerful than any human-made accelerator. The mechanism involves complex plasma physics, but the basic idea is this. The accretion disk, made of ionized gas, acts like a dynamo, generating magnetic fields as it rotates. These fields thread through the disk, and as the disk spins, they get twisted and amplified, wound up like a tightening spring. Eventually, the magnetic energy becomes so concentrated that it has to go somewhere. The fields act like railway tracks, guiding charged particles along their field lines. And because the strongest fields tend to align with the black hole's spin axis, particles get funneled upward and downward, away from the disk, forming the jets. As particles spiral along these magnetic field lines, they're accelerated to enormous speeds, sometimes 99.9% the speed of light or faster. This makes quasars the universe's most powerful particle accelerators. The Large Hadron Collider at CERN, humanity's greatest achievement in particle acceleration, can boost protons to 99.9999991% of light speed. That's extraordinarily fast, the result of billions of dollars and decades of engineering. But quasars do comparable accelerations naturally, across regions thousands of times larger, powered only by gravity and magnetism, following the laws of physics without any guidance or intention. And perhaps what's most remarkable is that these magnetic fields organize chaos. The accretion disk is turbulent, violent, seemingly random, but the magnetic fields threading through it create structure, create order, create the conditions for jets that remain coherent across millions of light years. Magnetism turns disorder into directed beams, chaos into geometry. Maybe that's nature's way. Even in the most violent environments, fields and forces create patterns, impose structure, find ways to channel energy along predictable paths. Pairs of quasars sometimes exist in merging galaxies, with two supermassive black holes orbiting each other while feeding. These binary quasars are relatively rare. We've only discovered a few dozen confirmed cases, but they're fascinating windows into how galaxies and their central black holes evolve. When two galaxies collide and merge, their central black holes don't immediately combine. Instead, they end up orbiting each other, separated by thousands or even tens of thousands of light years at first. Over time, gravitational interactions with surrounding stars and gas cause the orbit to decay, to shrink. The black holes spiral inward, getting closer and closer, their orbital period decreasing from millions of years to thousands, to eventually just hours or minutes. During this spiral, both black holes might be feeding, both accreting matter from the gas-rich environment of the merger. If both are accreting vigorously, we see two quasars, close together on the sky, each blazing with the light of infalling matter, their dancing partners in a gravitational waltz, each affecting the other's motion, each pulling on the surrounding gas, each contributing to the spectacular light show. Eventually these black holes will merge, creating gravitational waves that ripple through space-time. This merger will be one of the most powerful events in the universe, releasing more energy in a fraction of a second than the sun will produce in its entire lifetime, but all of it in gravitational waves, not light. After the merger, a single, more massive black hole remains, possibly kicked in some direction by the asymmetric emission of gravitational waves, eventually settling into the center of the new, merged galaxy. We haven't yet detected gravitational waves from supermassive black hole mergers. Our current detectors are sensitive to smaller black holes merging, but future space-based observatories should be able to detect these events. When they do, they'll observe the final moments of the dance we see beginning in binary quasars, the conclusion of a process that takes millions of years to unfold. And there's something almost poignant about these paired quasars, isn't there? Two galaxies, each with its own history, its own central black hole, its own story spanning billions of years, coming together. Their black holes orbit each other, feed together, shine together, before eventually merging into a single object. It's cosmic partnership on the grandest scale, a reminder that even black holes don't exist in isolation, that the universe is full of interactions, collaborations, mergers that transform what came before into something new. The light from quasars can be used as a cosmic ruler to measure the expansion rate of the universe at different epochs. This is one of the most important applications of quasars in modern cosmology. By comparing quasars at different distances, astronomers can trace how the universe's expansion has changed over time, mapping out cosmic history in unprecedented detail. The principle is somewhat like using lighthouses at sea. If you know how bright a lighthouse actually is, you can determine how far away it is by measuring how bright it appears. If it appears dim, it's far away. If it appears bright, it's nearby. The ratio tells you the distance. Quasars aren't quite standard candles. They vary in intrinsic brightness, but astronomers have found ways to use certain properties of quasars to estimate their luminosity, turning them into distance indicators. One method involves using the relationship between a quasar's luminosity and the velocity of gas orbiting in its accretion disk. More massive black holes have faster orbital velocities, and they also tend to be more luminous. By measuring the width of emission lines in the quasar's spectrum, which reflects the orbital velocity, astronomers can estimate the quasar's intrinsic brightness and then calculate its distance. With distances in hand, astronomers can map out how far away quasars were at different redshifts, and this tells them how the universe was expanding at different times. Combine observations from many quasars at various distances, and you get a detailed picture of cosmic expansion history. This has revealed that the expansion is accelerating, driven by something we call dark energy, one of the deepest mysteries in modern physics. Quasars have thus become tools for cosmology, beacons not just in space but in time, helping us understand the very evolution of the universe itself. They're not just interesting objects to study for their own sake. They're probes of cosmic expansion, dark energy, the large-scale structure of space-time. Every quasar observation contributes to our understanding of where the universe came from and where it's going. And perhaps that's the most profound use of light, not just to see objects, but to measure the fabric of space itself, to trace its expansion, to understand how the cosmos evolves. Quasars, shining across billions of years, give us the data to map cosmic history, to answer questions about the universe's past and future. Their light is information, encoded with details about distance, time, expansion, carrying messages that help us understand the biggest questions we can ask. Some quasars appear to change their type when viewed from different angles, suggesting we're seeing the same phenomenon differently. This discovery led to what's called the unified model of active galactic nuclei, an elegant idea that explains much of the diversity we observe in these objects. The basic concept is this. There's a thick torus of dust and gas surrounding the black hole and its accretion disk shaped like a donut. If you look at the quasar edge-on through the torus, the bright accretion disk is hidden. You see a dimmer object, sometimes classified as a different type of active galaxy. But if you look at the same quasar face-on looking down into the opening of the torus, you see the accretion disk directly, and it appears as a bright quasar. A thick torus of dust around the black hole can hide the bright accretion disk, making the quasar look quieter than it really is. The dust absorbs visible and ultraviolet light, preventing it from reaching us. What we see instead is infrared emission from the heated dust itself, the torus glowing because it's being illuminated by the hidden accretion disk inside. This unified model suggests that many of the different types of active galaxies we observe, quasars, Seyfert galaxies, radio galaxies, blazars, might be the same phenomenon viewed from different angles. The underlying physics is the same, a supermassive black hole accreting matter. But our viewing angle determines which components we see directly and which are hidden, creating an apparent diversity that's really just a matter of perspective. It's a bit like looking at a car. From the front, it looks one way. From the side, different. From above, different still. But it's the same car, just seen from different angles. Quasars might be similar, the same fundamental object appearing different depending on our line of sight. This realization simplified our understanding of active galaxies enormously. Instead of needing different explanations for dozens of types of objects, we have one basic model with variations based on viewing angle and other parameters. It's a unifying principle, showing that beneath apparent diversity lies fundamental similarity, that the universe's complexity often emerges from simple rules viewed from different perspectives. Quasars produce neutrinos, ghostly particles that can pass through entire planets without interacting with anything. Neutrinos are among the strangest particles in physics. They have almost no mass, no electric charge, and interact with matter so weakly that trillions of them pass through your body every second without you noticing. They're produced in nuclear reactions, in supernovae, and yes, in the extreme environments around quasars. Detecting these neutrinos gives astronomers a completely different window into the violent processes near the black hole. Unlike light, which can be absorbed or scattered, neutrinos travel straight through matter as if it weren't there. This means neutrinos from a quasar carry information about processes deep within the most obscured regions, places where light can't escape but neutrinos can. The challenge is detecting them. Because neutrinos interact so weakly, you need enormous detectors and long observation times to catch even a few. The IceCube Neutrino Observatory at the South Pole uses a cubic kilometre of Antarctic ice as a detector, looking for the faint flashes of light produced when a neutrino occasionally does interact with a water molecule. Other detectors use huge tanks of purified water or oil, all designed to catch these elusive particles. In 2018, IceCube detected a high-energy neutrino and traced it back to a blazar, a type of quasar with its jet pointed almost directly at Earth. This was the first time a neutrino had been definitively linked to a specific cosmic source outside our solar system. It opened a new era of multi-messenger astronomy, where we study the universe not just with light but with neutrinos, gravitational waves and other messengers. And perhaps neutrinos teach us something about persistence. They're so weakly interacting that they seem almost insubstantial, barely there. But they carry information that nothing else can carry, travelling through obstacles that would stop any other particle. Sometimes the quietest messengers, the ones that interact least, tell us the most about places we can't see any other way. The universe speaks to us in multiple languages, and neutrinos are one of its whispers, faint but carrying unique truths. The discovery of quasars helped confirm that Einstein's general relativity works even in the most extreme gravitational environments. When Einstein published his theory in 1915, it was a revolutionary new way of understanding gravity, not as a force, but as the curvature of space-time caused by mass and energy. The theory made predictions that seemed almost fantastical. Light should bend around massive objects, time should run slower in strong gravitational fields, orbits should slowly precess in ways Newton's theory couldn't explain. The behaviour of light and matter near quasars matches Einstein's predictions made decades before these objects were discovered. Near the supermassive black holes powering quasars, gravity is so intense that space-time is warped into shapes far more extreme than anything Einstein could have tested in his lifetime. And yet, the theory holds. Light bends exactly as predicted. Time dilates exactly as the equations say it should. The orbits of matter in the innermost regions of the accretion disk follow relativistic paths, precessing and evolving in ways that match general relativity's predictions. We can observe these effects directly. The X-ray emission from the inner accretion disk shows features, broad, skewed emission lines, that can only be explained by relativistic effects. Light being gravitationally redshifted as it climbs out of the deep gravitational well, light being Doppler shifted from matter, orbiting at significant fractions of light speed, light being focused and beamed due to the relativistic motion of its source. These features are fingerprints of general relativity, proof that Einstein's century-old equations still work in environments 1 billion times more extreme than anything he could have imagined. And perhaps there's something deeply satisfying about that. Einstein worked out these equations using pure thought, mathematics, and logical consistency. He had no observations of black holes, no data from quasars. He was guided by theoretical principles, the equivalence of gravity and acceleration, the constancy of the speed of light, the need for mathematical elegance, and yet, decades later, when astronomers finally observed the most extreme gravitational environments in nature. They found Einstein's theory waiting there, accurately describing what they saw. It's a testament to the power of mathematics and theoretical physics, the way the right equations can describe aspects of reality their creators never witnessed. Einstein gave us the tools to understand quasars before quasars were discovered, before we even knew such extreme objects could exist. His theory has been tested in every way we can imagine, from GPS satellites orbiting Earth to the detection of gravitational waves from merging black holes, and it keeps passing every test. Quasars are just one more confirmation, one more environment where space-time behaves exactly as Einstein said it would. Quasars can heat the gas in galaxy clusters, preventing it from cooling and forming new stars. This feedback mechanism helps explain why the most massive galaxies stopped growing billions of years ago. It's a story about balance, about how the universe regulates itself on the largest scales. Galaxy clusters are the biggest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, all held together by gravity. Between the galaxies floats hot gas, millions of degrees hot, filling the space within the cluster. This gas is X-ray bright, and it contains more mass than all the stars in all the galaxies combined. In principle, this gas should cool over time, radiating away its energy. As it cools, it should become denser, eventually collapsing and forming new stars, feeding the growth of the central galaxy. But in many clusters, this doesn't happen. The gas stays hot. Star formation in the central galaxies largely ceased billions of years ago. Why? The answer often involves the supermassive black hole at the center of the cluster's largest galaxy. Even though this black hole might not be accreting vigorously enough to qualify as a quasar anymore, it's still active. It produces jets, relativistic outflows that pump energy into the surrounding gas. These jets create bubbles, cavities in the hot gas, visible in X-ray images. As the jets inflate these bubbles, they do work on the gas, heating it, stirring it, preventing it from cooling and collapsing. It's a heating mechanism powered by the black hole's accretion, even at relatively low rates. The black hole eats a little, produces jets, heats the gas, which prevents the gas from cooling and feeding the black hole more. It's a self-regulating cycle, a thermostat on a cosmic scale, and this helps explain one of the puzzles of galaxy evolution. Why do the most massive galaxies seem to have stopped growing? Why aren't they still forming stars vigorously, given all the gas available? The answer is feedback. The central black hole, through its jets and radiation, heats the surrounding gas and prevents it from forming stars. The galaxy and black hole reach an equilibrium where growth largely ceases. It's a beautiful example of how different scales in the universe connect. A black hole, even a supermassive one, is tiny compared to a galaxy cluster. But its influence, mediated through jets and radiation, can affect gas across millions of light years, regulating star formation, shaping the evolution of entire clusters. Perhaps this is one of nature's recurring patterns, small engines with far-reaching effects, feedback loops that maintain balance, systems that regulate themselves without any conscious guidance. The radio lobes created by quasar jets can be larger than the galaxy itself, extending for millions of light years. These vast structures are fossils of ancient quasar activity, glowing faintly with energy injected millions of years ago. When a quasar is actively producing jets, those jets plough through the intergalactic medium, pushing gas aside, creating shock waves. At the ends of the jets, where they finally collide with the surrounding gas and stop, particles pile up and create glowing lobes visible in radio wavelengths. Even after the quasar itself fades, even after the jets shut off and the accretion disk thins, these lobes remain. They're filled with relativistic particles and magnetic fields, and they continue to emit radio waves for millions of years as they slowly expand and fade. Some radio lobes extend for 10 million light years or more, spans larger than the distance between our galaxy and Andromeda, regions so vast that light takes 10 million years to cross them. These lobes tell us about the quasar's history. By studying their size, shape, and radio brightness, astronomers can estimate how long the jets were active, how powerful they were when they shut off. The lobes are like archaeological sites preserving information about events that ended long ago. A galaxy might look quiet now, its central black hole dormant. but the presence of giant radio lobes tells us it was once a powerful quasar, that jets once screamed outward at nearly the speed of a light. And there's something almost melancholic about these radio fossils. They're ghosts of former violence, echoes of an active past, slowly fading as the relativistic particles lose energy and the magnetic fields decay. They're reminders that nothing lasts forever, that even the most powerful phenomena eventually fade into whispers, into faint emissions detectable only by sensitive instruments. But they're also beautiful in their way. Vast, intricate structures shaped by physics and time, visible across enormous distances, testifying to events that happened when the universe was younger. They connect past to present, showing us that the quiet galaxies we see today were not always quiet, that the universe's history is written not just in light but in radio emissions, in the fading glow of ancient jets, in structures that persist long after the engines that created them have gone silent. Quasars show us that supermassive black holes and their host galaxies grow together, influencing each other's evolution. This cosmic partnership means that understanding galaxies requires understanding the monsters at their hearts. For decades, astronomers treated black holes and galaxies as separate subjects. Galaxies were about stars, gas, dark matter, the large-scale structure. Black holes were exotic objects in their own right, interesting for their extreme physics but somewhat disconnected from the galaxy around them. Then, in the 1990s and 2000s, a remarkable pattern emerged. Astronomers found a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, particularly the velocity dispersion of stars in the central bulge. Galaxies with massive black holes had fast-moving stars in their centres. Galaxies with smaller black holes had slower-moving stars. The correlation was tight, suggesting a deep connection. This was surprising because the black hole is tiny compared to the galaxy. The black hole's gravitational influence extends only a few light-years at most, while the galaxy spans hundreds of thousands of light-years. How does the black hole know about the galaxy? How does the galaxy know about the black hole? They must be growing together, influencing each other through feedback processes. During the quasar phase, when the black hole is feeding vigorously, its radiation and jets affect the entire galaxy. They heat gas, drive winds, trigger or suppress star formation. These effects regulate the black hole's own growth by controlling how much gas can fall inward. At the same time, the galaxy's evolution through mergers, gas accretion from the intergalactic medium star formation, determines how much fuel is available for the black hole. It's a two-way street, a dialogue between galaxy and black hole spanning billions of years. They co-evolve, each shaping the other's growth, maintaining the observed correlations. This means that to truly understand how galaxies form and evolve, we can't ignore the central black hole, and to understand black hole growth we can't ignore the galaxy around it. Perhaps this partnership teaches us something about interconnectedness. In a universe governed by gravity, nothing is truly isolated. The smallest components affect the largest structures, and vice versa. A black hole weighing a few billion solar masses influences a galaxy containing hundreds of billions of stars, and that galaxy, through its mergers and gas flows, feeds and regulates the black hole. They're partners in evolution, their fates intertwined across cosmic time. The spectrum of a quasar contains information about all the material its light passed through on its journey to Earth. Each quasar is like a cosmic core sample, revealing the composition of space across billions of years. When we analyse a quasar's spectrum in detail, we're not just learning about the quasar itself, we're learning about everything between us and it, every cloud of gas, every intervening galaxy, every trace of matter the light encountered on its journey. This makes quasars invaluable for studying the history of the universe's chemical enrichment. Stars create heavy elements in their cores and disperse them through space when they die, especially in supernova explosions. Over cosmic time, the abundance of heavy elements, metals in astronomers' terminology, increases. By studying absorption lines in quasar spectra at different redshifts, astronomers can trace how metal abundance has changed over billions of years. They've found that even in the early universe, some gas clouds were already enriched with metals, suggesting that stars formed, lived and died quite early in cosmic history. They've found that metals are not uniformly distributed. Some regions are more enriched than others, reflecting the complex history of star formation and gas flows. They've traced how carbon, oxygen, silicon, iron, and other elements built up over time, painting a picture of chemical evolution. Each quasar spectrum is a journey through time and space. The quasar itself, the emission we see, tells us about conditions in the early universe, about black hole growth and galaxy evolution. The absorption lines tell us about everything in between, about gas clouds at various distances, about the intergalactic medium, about galaxies that happen to lie along the line of sight. It's layer upon layer of information, like reading a tree's rings to learn about climate history, except here we're reading light to learn about cosmic history. And perhaps what's most remarkable is that all this information is encoded in something as simple as a spectrum, a rainbow of light, broken into its component wavelengths, marked by bright emission lines and dark absorption lines. It looks like a simple graph, a plot of brightness versus wavelength. But embedded in that graph is the story of billions of years, the composition of matter across half the observable universe, the record of how elements formed and spread, how gas moved and evolved. Every quasar spectrum is a cosmic document waiting to be read. Some quasars turn on and off over timescales of tens of thousands of years, possibly due to changes in their fuel supply. These changing-look quasars suggest that the boundary between active and quiet black holes is more fluid than we thought. For a long time, astronomers assumed that quasar activity changed slowly, over millions or even billions of years. The black hole would feed during one era, then gradually run out of fuel and fade into dormancy. It seemed like a one-way street, or at least a very gradual transition. But in recent years, astronomers have discovered quasars that change dramatically over much shorter timescales, years to decades in some cases. A quasar that appeared bright and active in one survey might look dim and quiet just a decade later. Or a previously quiet galaxy suddenly brightens, its central black hole turning on and beginning to shine as a quasar. These changes happen far too quickly to be explained by gradual fuel depletion. What's causing these rapid transitions? The most likely explanation involves changes in the accretion rate. Perhaps a clump of gas or a star wanders too close to the black hole, providing a sudden influx of fuel. Perhaps instabilities in the accretion disk cause the feeding rate to fluctuate. Perhaps the disk goes through cycles, alternating between high and low states, like a cosmic heartbeat with periods of tens of thousands of years. These changing-look quasars are valuable because they allow us to study the physics of accretion in real time, or at least on timescales comparable to human civilization. We can observe the same object in different states, bright and dim, and compare them to understand what changed. It's like catching a system in the act of transitioning, seeing the gears of the mechanism as they turn, and there's something almost humanizing about these changes, isn't there? We often think of cosmic phenomena as eternal, unchanging, operating on timescales so vast that they might as well be static from our perspective. But changing-look quasars remind us that the universe is dynamic, even on accessible timescales. Things change. Black holes wake up and go back to sleep. The cosmos is not frozen in time, but constantly shifting, evolving, transitioning between states. Perhaps that makes it more real, more alive, knowing that if we watched long enough, generations certainly, but not geological ages, we might actually witness a black hole turn on or off, see a galaxy transform before our telescopic eyes. The jets from quasars can trigger star formation in distant galaxies by compressing gas clouds as they pass. Destruction and creation work hand in hand, with quasars both stopping and starting the birth of stars. We've already talked about how quasar feedback can halt star formation, heating gas and driving it away. But the relationship between quasars and star formation is more nuanced, more interesting than simple suppression. When a quasar jet plows through a galaxy, it doesn't just heat gas, it also compresses it. And compressed gas, if it's dense enough and cool enough, can collapse under its own gravity and form stars. So while the jet's overall effect might be to heat the surrounding medium and suppress star formation on large scales, locally, at the edges of the jet, or in regions where it compresses gas without heating it too much, star formation can actually be triggered. Astronomers have observed this in several systems. They see young stars forming along the edges of radio lobes, in regions where the jet has compressed the gas. They see enhanced star formation rates in galaxies intersected by quasar jets. It's positive feedback in certain locations, even while negative feedback dominates elsewhere. This dual nature, suppressing here, triggering there, makes quasars complex sculptors of their environments. They're not just destroying or creating, they're doing both simultaneously, depending on local conditions. A single quasar might shut down star formation in its host galaxy's core while triggering bursts of star formation in nearby satellite galaxies or along the jet's path. And perhaps this complexity is more realistic, more honest about how nature works. Simple narratives, quasars destroy or quasars create, are appealing but incomplete. The truth is messier, more contextual. The same phenomenon can have opposite effects depending on where you look, on local conditions, on the details of gas density and temperature and magnetic fields. The universe doesn't usually deal in absolutes. It deals in competing processes, in balances, in outcomes that depend on dozens of variables. Quasars embody that complexity, showing us that even in the most extreme environments, the effects are mixed, the story is nuanced, the outcome depends on where you're standing. Quasars exist in a range of sizes and brightnesses, from those barely more luminous than normal galaxies to ones outshining thousands of galaxies. This diversity suggests that many factors, black hole mass, spin and feeding rate, combine to create each quasar's unique properties. Not all quasars are equal. Some are monsters, blazing with the light of 1 trillion suns. Others are more modest, perhaps only 100 billion times the sun's luminosity, still extraordinarily bright by any reasonable standard, but faint compared to their more luminous cousins. This range reflects the diversity of conditions under which quasars form. The black hole's mass matters. More massive black holes can accrete more matter and potentially shine brighter. The black hole's spin matters too. A rapidly spinning black hole can extract energy more efficiently from infalling matter, producing more luminosity for the same accretion rate. And the feeding rate is perhaps most important. A black hole that's gorging itself will shine far brighter than one that's only nibbling at a trickle of gas. Then there are environmental factors. Is the quasar in a gas-rich galaxy with abundant fuel? Is it experiencing a major merger that funnels gas toward the centre? Is it isolated, relying on whatever gas happens to wander by? All these factors influence how bright the quasar becomes and how long it remains active. The result is a population of quasars spanning several orders of magnitude in luminosity. When astronomers survey the sky, they find everything from barely quasar objects at the faint end to stupendously bright ones at the other extreme. And this diversity is actually useful. It allows us to study how quasar properties correlate with their environment, their host galaxies, their place in cosmic history. Perhaps the lesson here is that even within a single category, quasars, there's tremendous variation. No two are exactly alike. Each represents a unique combination of black hole properties, fuel supply, environment, and evolutionary state. The universe doesn't mass-produce identical objects. It creates variations on themes, each quasar a unique expression of the same underlying physics operating under different conditions. And that diversity, that individuality, is part of what makes them endlessly fascinating to study. Every quasar has its own story, its own particular combination of circumstances that made it what it is. The study of quasars revealed that the universe is much larger, older, and more energetic than astronomers thought in the early 20th century. These objects expanded our cosmic horizons both literally and figuratively, showing us a universe of almost unimaginable scale. Before quasars, astronomers were still grappling with the true size of the universe. Edwin Hubble had shown in the 1920s that many nebulae were actually distant galaxies, pushing our cosmic horizons far beyond the Milky Way. But even so, the universe seemed somewhat sedate, populated by galaxies quietly forming stars, evolution happening on timescales of billions of years. Quasars shattered that tranquility. They showed that the universe contained objects with luminosities that dwarfed anything previously observed. They demonstrated that violent energetic processes were happening in galactic centers. They revealed that the early universe was a more chaotic, active place than the local neighborhood we can study in detail. And their enormous distances proved that the universe was bigger than many had imagined, billions of light years across at minimum, perhaps infinite. This expansion of horizons wasn't just about numbers, it was about possibility, about what the universe could do. Before quasars, there were limits to what seemed plausible. An object outshining 100 billion stars from a region smaller than a solar system? Impossible. Jets travelling at 99.9% the speed of a light for millions of light years? Absurd. Black holes with masses of billions of suns? Unfathomable. But quasars forced astronomers to accept that all these things were not only possible but actually occurring. It's a humbling realization, and an exciting one. The universe is not constrained by our intuitions or our imagination. It's bigger, stranger, more extreme than we typically envision. And every time we think we've grasped its scale, something new, quasars, dark energy, gravitational waves, comes along to show us we were still thinking too small, still imagining too timidly. Perhaps that's one of the great gifts of astronomy. It constantly expands our sense of scale, of possibility, of what the cosmos can do. We start with the world around us, familiar and comprehensible. Then we learn about planets, stars, galaxies, each step taking us further, showing us larger structures, longer timescales, greater energies. Quasars were another step in that journey, another expansion of horizons, another lesson that the universe is grander than we dare to dream. Quasar jets can remain coherent and focused for millions of light years, a feat of natural engineering we still don't fully understand. The physics keeping these narrow beams stable across such distances involves processes we're only beginning to grasp. Think about trying to maintain a narrow beam of water from a garden hose across even a few meters. The stream breaks up, spreads out, becomes turbulent and dispersed. That's what we'd naively expect to happen with quasar jets too. The particles should spread out, the beam should widen, turbulence should tear it apart, but they don't. Jets remain narrow, focused, beam-like across distances of millions of light years. They maintain their structure from the black hole all the way to the terminal shock where they finally collide with intergalactic gas and stop. The collimation, the focusing into a narrow beam, is remarkable and not fully understood. Part of the answer involves magnetic fields. We know that magnetic fields thread through the jets, and these fields can help confine the flow, keeping particles moving along field lines rather than spreading sideways. But the details are complex. How do the magnetic fields maintain their structure over such distances? How do they avoid instabilities that should tear the jet apart? What role does the surrounding medium play in confining the jet? These are active research questions. Simulations help, showing that under certain conditions, magnetically dominated jets can remain stable over large distances. Observations help too, revealing details of jet structure, kinks and bends and patterns that tell us about the forces at work. But a complete understanding remains elusive, a puzzle still being solved. And perhaps there's something wonderful about that, about the fact that even after decades of studying quasars, they still hold mysteries, still present phenomena we can't fully explain. The universe is not obligated to make itself easy to understand. It presents us with challenges, with structures and processes that push our physics to its limits. Quasar jets are one of those challenges, natural phenomena that demonstrate principles we're still working to grasp, reminding us that for all our progress, for all our understanding, there are still cosmic wonders that exceed our current theories, still phenomena waiting to be fully explained. The environments around quasars are some of the best places in the universe to test theories of extreme physics. Nowhere else do we find such intense gravity, radiation, magnetic fields and velocities all concentrated together. It's a natural laboratory, operating at scales and energies we could never reproduce on Earth, allowing us to test our theories under conditions that push them to their breaking points. Consider the gravity near a quasar's black hole. Space-time is curved so severely that the familiar rules of Newtonian physics completely break down. Objects don't move in simple ellipses. They follow complex relativistic orbits that precess and spiral in ways Newton never imagined. Time itself runs at different rates depending on how deep you are in the gravitational well. Light bends, redshifts, gets focused and lensed by the warped geometry of space-time. Then there's the radiation. The flux of photons near a quasar is so intense that radiation pressure becomes a significant force, pushing on matter with strength comparable to gravity itself. This is a regime where light doesn't just illuminate, it sculpts, it shapes, it drives material flows. The radiation field is so energetic that it keeps matter ionized, strips electrons from atoms. heats gas to temperatures where it exists as plasma. The magnetic fields are equally extreme, millions of times stronger than anything we experience on Earth. At these field strengths, magnetic forces dominate over other interactions. The fields channel flows, accelerate particles, generate electricity on cosmic scales. They create conditions where quantum effects, like pair production, where intense fields can create matter and antimatter out of pure energy, might actually occur. And the velocities, jets moving at 99.9% of light speed, matter in the inner accretion disk orbiting at similar speeds. At these velocities, relativistic effects are dramatic. Time dilates, lengths contract, masses increase. The physics is no longer the comfortable regime of everyday experience, but the strange world of special relativity, where simultaneity is relative and cause and effect get complicated. All these extremes together create conditions we simply cannot replicate in laboratories. The most powerful particle accelerators, the strongest magnetic fields we can generate, the most intense lasers we can build, all pale in comparison to what happens naturally near quasars. So we study them, using their extreme environments to test whether our theories still work when pushed to the limits, whether the equations we derive for modest conditions still hold when gravity, magnetism and velocity all reach their maxima. And remarkably, our theories do hold. General relativity still works, electromagnetism still works, quantum mechanics, where we can test it, still works. The laws of physics don't change just because the environment is extreme. Perhaps that's the deepest lesson quasars teach us, that the universe operates by consistent rules, that the physics we discover here on Earth applies across billions of light years, across conditions spanning orders of magnitude in energy and scale. The universe is comprehensible, governable by laws we can discover and test. Quasars are the proof. Modern surveys have discovered hundreds of thousands of quasars, creating a census of supermassive black holes across cosmic history. This population study reveals when black holes were most active and how their era of dominance ended. In the early days of quasar astronomy, each discovery was a major event, carefully studied, analysed in detail. But modern digital sky surveys, automated telescopes taking millions of images, computers analysing spectra by the thousands, have transformed quasar science into a statistical enterprise. We now know the locations and properties of hundreds of thousands of quasars spanning a wide range of distances and cosmic epochs. This large sample allows astronomers to ask population-level questions. How many quasars existed at different times in cosmic history? How has the typical black hole mass changed over time? What's the relationship between quasar activity and galaxy mergers? How does the quasar population correlate with the large-scale structure of the universe? The answers paint a detailed picture of black hole evolution. The quasar population peaked about 10 billion years ago, when the universe was roughly a quarter of its current age. Before that peak, the universe was too young. Galaxies were still forming, black holes were still growing. After that peak, quasar numbers declined as fuel became scarcer, as galaxies spread apart, as the most massive black holes exhausted their food supply. This census also reveals diversity. Not all quasars are the same. There are radio-loud quasars with powerful jets, and radio-quiet ones without obvious jets. There are broad-line quasars where we see the accretion disk directly, and narrow-line ones where dust obscures the central engine. There are blazars where the jet points nearly at us, and radio galaxies where we see the jets from the side. Each type represents different viewing angles, different physical conditions, different stages of evolution. And this statistical approach has become essential for modern astronomy. We can't learn everything from individual objects. We need populations, samples large enough to reveal trends and correlations. The hundreds of thousands of known quasars allow that kind of analysis, letting us see patterns that emerge only when you have enough examples to average over, to compare, to categorize. Perhaps there's something democratizing about this. Early astronomy was about individual objects. This star, that planet, that galaxy. Modern astronomy is increasingly about populations, distributions, correlations, statistical properties. Every quasar contributes to our understanding not just as an individual object, but as a member of a population, a data point in a larger pattern, one voice in a cosmic chorus that together tells the story of how black holes grew and evolved across billions of years. Quasars may have helped seed the intergalactic medium with heavy elements created in stars, enriching the cosmic gas. Their powerful winds scattered the periodic table across space, providing the raw materials for future generations of stars and planets. Stars create heavy elements in their cores through nuclear fusion. Hydrogen fuses into helium, helium into carbon and oxygen, and in the most massive stars the process continues all the way up to iron. When stars die, especially in supernova explosions, they eject these elements into space, enriching the interstellar medium with metals. But how do these elements get from inside galaxies out into the intergalactic medium, the vast spaces between galaxies? This is where quasars come in. Their powerful winds, driven by radiation pressure and jets, can expel gas from galaxies entirely. And that gas carries with it the heavy elements forged in stars: carbon, nitrogen, oxygen, silicon, iron, all the elements essential for rocky planets and organic chemistry. Observations support this. When astronomers study absorption lines in quasar spectra, they find metals even in the intergalactic medium, far from any visible galaxy. The gas between galaxies isn't pure primordial hydrogen and helium, it's been enriched with heavier elements, and the distribution of these metals correlates with where quasars and active galaxies have been, suggesting that feedback from these objects helped to spread elements through space. This enrichment has profound consequences for cosmic evolution. The first stars formed from pure hydrogen and helium, the primordial elements created in the Big Bang. But later generations of stars formed from gas enriched with metals, and this changes their properties. Metal-rich gas cools more efficiently, allowing smaller, sun-like stars to form. Metals in protoplanetary disks allow rocky planets to condense. And of course, carbon, nitrogen, oxygen, the elements of life, need to be present for organic chemistry to happen. So in a very real sense, quasars helped prepare the universe for planets and life. By driving winds that ejected metal-enriched gas, by spreading elements far and wide, they ensured that later generations of star formation would have access to the full periodic table, not just hydrogen and helium. They scattered the seeds, literally the atomic seeds, from which future worlds would grow, and perhaps there's something poetic about that. The most violent, destructive processes in the universe, black holes tearing apart matter, radiation strong enough to blow entire galaxies apart, jets screaming through space, these same processes enrich the cosmos, making possible the complex chemistry that eventually led to planets, to life, to consciousness capable of looking back and understanding where it came from. Destruction and creation intertwined, as they so often are in nature. We may be living in a universe where quasar-like activity will never occur again, as galaxies run out of fuel and drift apart. The age of quasars may be permanently behind us, a brief but spectacular chapter in cosmic history. The universe is expanding, and in our current epoch that expansion is accelerating, driven by dark energy. As space expands, galaxies that aren't gravitationally bound to each other drift apart, increasing the distance between them. This expansion has consequences for the future of quasars. Galaxy mergers, one of the main triggers for quasar activity, will become less common as galaxies spread apart. The local group, the small cluster containing the Milky Way, Andromeda, and a few dozen smaller galaxies, is gravitationally bound and will eventually merge. But beyond the local group, most galaxies are already too distant and receding too fast to ever interact with us. The universe is becoming more isolated, more sparse, and within galaxies the fuel supply is finite. Stars are gradually consuming and locking up the gas. Some gas is expelled by stellar winds and supernovae. The gas that remains is often too hot or too diffuse to easily fall into the central black hole. Without mergers to funnel new gas inward, without a fresh supply of fuel, most supermassive black holes will remain dormant, never awakening into quasar activity again. There might be occasional flickers, a star wandering too close to a black hole, creating a brief flare. Or perhaps in the distant future, when the Milky Way and Andromeda merge, their central black holes will feed briefly, producing one last gasp of quasar-like activity. But by and large, the era of quasars is over. We live in the aftermath, in a universe past its most luminous, most violent phase. This is both melancholic and peaceful. The wild youth of the universe is behind it. The cosmos is entering a long middle age of gradual star formation, slow evolution, increasing quiet. Eventually, on timescales of trillions of years, even stars will stop forming as the last gas is consumed. The universe will dim, cooling into a dark, sparse future dominated by dead remnants and ever-increasing separation. But we're here now, in this intermediate epoch, when stars still shine, when we can still see the light from ancient quasars, when the universe retains echoes of its violent past while settling into a calmer present. Perhaps that's the best time to be alive, cosmically speaking. Late enough that the universe has calmed down enough for life to emerge, early enough that there's still beauty to see, still light from the ancient past reaching us, still stories written in starlight for those who know how to read them. Despite decades of study, quasars still hold mysteries about how their black holes grew so fast, how their jets stay focused, and what they tell us about the deepest nature of gravity and space-time. They remind us that the universe is far stranger and more wonderful than we can yet fully comprehend, with secrets still waiting in the darkness between stars. We've learned so much. We understand that quasars are powered by supermassive black holes. We know their light comes from accretion disks heated by friction. We've mapped their jets, measured their distances, catalogued hundreds of thousands of them. We've used them to study cosmic expansion, to trace the distribution of matter in the early universe, to test general relativity in extreme conditions. The progress has been remarkable, and yet fundamental questions remain. How did black holes grow to billions of solar masses in the first billion years of cosmic history? The timescales seem too short, the mechanisms unclear. We have theories: super Eddington accretion, direct collapse of massive gas clouds, chains of mergers, but no definitive answer. The rapid growth of early quasar black holes remains puzzling. How do jets remain stable across millions of light years? We know magnetic fields are involved, but the detailed physics of jet collimation, the mechanisms preventing instabilities, the reason jets don't simply spread out and dissipate, these are still active research areas. We have simulations, partial answers, but not complete understanding. And what can quasars teach us about quantum gravity, about what happens at the event horizon, about the ultimate fate of information? These questions touch on the deepest unsolved problems in physics: how to reconcile quantum mechanics and general relativity, whether information is preserved in black holes, what the universe is like at the smallest scales and highest energies. Quasars provide a cosmic laboratory, but the experiments are difficult to interpret, the observations indirect. Perhaps this is how it should be. Science is not about reaching a final answer and stopping. It's about continuous discovery, about each answer revealing new questions, deeper mysteries. Quasars have taught us so much, expanded our understanding in profound ways, and they continue to challenge us, to present puzzles we haven't yet solved, to hint at physics we don't yet fully grasp. They remind us that the universe is far stranger and more wonderful than we can yet fully comprehend, with secrets still waiting in the darkness between stars. And maybe that's the best gift they can give us. Not just knowledge, but the assurance that there's always more to learn, more to discover, that the cosmos will never run out of wonders, that we'll never reach a point where we've figured it all out and there's nothing left to explore. The universe is generous with its mysteries, and quasars are among its most magnificent puzzles, shining across billions of light years, carrying questions we're still learning how to answer. And so, we've travelled through 50 facts about quasars, these cosmic beacons shining from the early universe, powered by supermassive black holes feeding on matter, in a brilliant display that outshines entire galaxies. We've seen how they helped prove the universe is expanding, how they cleared the cosmic fog during ionization, how they shape the evolution of galaxies through feedback and winds. We've glimpsed their jets travelling at nearly light speed, their accretion disks glowing hotter than any star, their influence extending across millions of light years. Quasars remind us that the universe operates on scales that dwarf our everyday experience, scales of energy, distance, and time that challenge our intuition and expand our sense of what's possible. They show us that the cosmos was once wilder, more violent, more luminous than it is today, and they demonstrate that even the most extreme phenomena follow natural laws, obey equations we can write down and test, connect to the physics we discover here on Earth. Perhaps most remarkably, they show us the past. Every quasar we observe existed billions of years ago when the universe was young. Their light has travelled across cosmic history to reach our telescopes tonight, carrying information about epochs we could never visit, about conditions at the edge of space and time. They're messengers from the ancient universe, and we're fortunate enough to live in an era when we can receive those messages, decode them, learn from them. As you drift towards sleep tonight, you might think about those distant lights, still travelling through space, still carrying their messages. Some of them left their sources before Earth existed, before the sun ignited, journeying through billions of years of cosmic expansion to arrive here, now, falling gently onto telescope mirrors and into human awareness. The universe speaks to us across unimaginable distances, and we've learned to listen, to understand, to piece together the story it's telling. Sweet dreams, and remember, the brightest things in the universe shine for us still, across the darkness, across the years. Patient messengers waiting to share their secrets with anyone curious enough to look up and wonder.